Hey everyone, in this video we're going to work through a couple more examples here. So the times in the 40-yard dash for a group of running backs in the NFL Combine are normally distributed with an average time of 4.8 seconds and a standard deviation of 0.17 seconds. The top 10% will probably be drafted. We want to know what time should we get to be in that top 10%. Now I specifically picked this problem because top 10% can mean different things depending on the situation. The top 10% of scores on the SATs is going to be the largest of the scores. The top 10% for a 40-yard dash, which is a race, is going to be the smallest 10% of values. And that's something that we have to keep in mind. So when we draw our picture of this normal curve, we have our 4.8 is the center here. We're going to add 0.17. That's going to give me 4.97. And then we add another 0.17. That's going to give me 5.14, and we add one more 0.17. That's going to give me 5.31. Now we can also subtract 0.17 to get the one standard deviation below the mean. That's going to be 4.63. We subtract another 0.17 to get 4.46. And we subtract another 0.17 to get 4.29. And we could use the empirical rule, okay? But we want the top 10%. So again, the top 10% for a race is going to be the lower values on the graph, not the bigger values. If you're getting a 5.14, you are slower than the other people doing the 40-yard dash, so you wouldn't be considered top 10. So I want top 10%, so I want 0.1 down here. If I wanted the top 10% of SAT scores, then I would want 0.9, all the area below this value, where the 0.1 is up here, is the remaining values. And so it depends on the values of, it depends on the context of the problem, which you're going to choose. So I think because we're at 0.1, the answer is going to be somewhere between 4.46 and 4.63. Again, this is always a good exercise to engage in, estimating what you think the value is going to be so that you know if your answer makes sense. When you're plugging stuff into the computer and asking it for answers, you don't always know like what you're getting is good, and so it's nice to have an idea beforehand. So again, we're going to put the probability, we need the mean, and we need the standard deviation. So the probability we talked about, because it's the top 10%, we're going to use 0.1. Usually, if it were the top 10%, we would use 0.9 because that's the area below the top 10%. But in this case, the top 10% is really the bottom 10% of times. And so again, that's something that you need to watch out for. We know that 4.8 is the mean and the standard deviation is 0.17. So the probability that, or the time that you have to get so that you're in the top 10% is going to be NORM.INV. I'm going to use 0.1, comma, 4.8, comma, 0.17. And that gives me a 4.58, which I believe was in the interval that I had guessed it would be in. Yeah, between 4.46 and 4.63. There we are. So now, I'm going to keep this up for my next drawing, for this next example. We want to know what two z-scores found the middle 50 0.25% of a normal distribution. Now, as soon as I hear the word z-scores, and what we're trying to find are z-scores along the bottom of a curve, along the bottom here of this curve, if we're talking about z-scores, then this is the standard normal curve. So when you see z-scores, we're talking about the standard normal curve. And the standard normal curve has a mean of 0 and a standard deviation of 1. And so that's a really easy graph to label. And we're looking for the middle 55%. The middle 55% is going to be in here because I know that one standard deviation away is 68%. So the middle 55% is going to be right in here, okay? And if I split that in half evenly, because this is symmetric, this is 25% right here, and this is 25% right here. Now we know that from negative infinity all the way up to the middle, that's 50%, or 0.5. And all the way to here is what I'm looking for to plug in for my probability for this problem. What two z-scores bound the middle 55%. So to find this proportion, I'm going to take this proportion, which is 0.25. I'm going to subtract it from 0.5. That leaves me with 0.25 below this value. Now, since this is symmetric, whatever I get for this z-score, it'll be negative, is going to be the same as this z-score. But if I just wanted to find this value, this z-score right here, I would take the 50% and I would add another 0.25 to it. And the proportion to find this, my probability, would be equal to 0.75. So now let's go ahead and calculate this. So I'm going to take, for my lower bound probability, I'm going to get one value. For my upper bound probability, I have a different value. So for my upper bound probability, we said that was going to be 0.25. And for my upper bound, we said that was going to be 0.75. And again, it's the picture. We want the proportion, we want the area to be below the value that we're looking for. So we want this area here, which is going to be 0.25. If this is 0.5 and this is 0.25, then this area is going to be the other 0.25 right here. So then we also need the mean and the standard deviation. And since this is the standard normal curve, because it says z-scores, I know that the mean is 0 and the standard deviation is 1. So to find the lower bound, I'm going to do norm.inverse, and that's going to be this proportion, this mean, and this standard deviation, and that's going to spit out negative 0.674. If I want to find the upper bound, I'm going to put in 0.75. Oh, wait. I've been doing this all wrong. We want the middle 55%. I'm sorry. So the middle 55%, these values are, I'm sure you were watching this saying, wait a second, that doesn't add up. So I apologize. The middle 55%, if we split 55 in 2, we get 27.5%, right? So this would be 0.275. And then 0.5 minus 0.275 would be 0.225. My apologies for that. Oh, geez. Okay. So I'm actually plugging in 0.225 for this. for this one. And that would mean 50 plus another 0.275 for the upper one wouldn't be 75%, it'd be 0.775. Again, my apologies for that. 0.775, there we go. So, now we're getting negative 0.75 or negative 0.755. If we find this same value, I'm just gonna copy and paste this. And if I copy and paste it, the formula should all be in the right spot. And you notice this time I get a positive 0.755. So these z-scores have the same absolute value because of the symmetry. One is just negative, the other one's positive. So we get negative 0.755 and positive 0.755 for my two z-scores. All right, so I think we get the idea of the picture. So I'm just gonna work in Excel for the rest of these. A professor says that only the top 8% of a class get an A. The class average will be a 72 with a standard deviation of 12. What grade do you need to get an A? All right, so again, only the top 8%. So if the top 8% is all the way to the right, how much percent is below that? That's gonna be 92%. So my probability is gonna be 0.92. The mean is gonna be 72, and the standard deviation is going to be 12. So we want the probability that we get below a 0.92, just so we know what that's, or so we get below an A, so we know what the value is for the cutoff for an A. And so we're gonna do norm.inverse of these three values. And so the cutoff for an A is going to be an 88.86. And so I'm going to say you would need to get an 89 or better in the class to get an A. Now I know that an 89 is not an A traditionally, but this professor is curving the scores, so he's making sure that 8% are the only ones, the top 8% are the only ones that get A's. And with the average given and the standard deviation, an 89 would get me into that top 8%. So now, the bottom 12% get an F. What grade would you need to get a D or better? All right, well this is, again, easy. The bottom 12%, that's already all the stuff that's on the bottom, the smaller values. And so I can just leave that, the 0.12. But the mean and standard deviation are gonna stay the same. And so my norm.inverse function, again, I can just copy this and paste it, and I've got my new set of numbers. So what grade would you need to get a D or better? Well, the 57.9 is the cutoff for an F. So I would want, you would need to get a 58 or better in order not to fail, which is really what the question's asking.